Hi everyone, welcome to another episode of AVUSD Storytime Science. I'm Mrs. Gillette. Today's story is Things That Float and Things That Don't, written by David Adler, illustrated by Anna Raff. Today's story is read by Sophia Aguilera, AVCI Explainer, class of 2020. Have you ever wondered why some things float on the surface of water and other things sink to the bottom? What about why a boat made out of aluminum foil floats even when you pile paper clips on top? But when you take that same piece of aluminum foil and crumple it up, it sinks to the bottom. In this story, the science behind this phenomena is explained. I want you to listen carefully about the scientific explanation of density and flotation. Also, make some text-to-self connections. What have you observed in your everyday life with the objects around you? What objects float and what don't? Be sure to join Mrs. Swearingen after the story for activities relating to density and flotation that you can do at home with your family. See you soon.
Things That Float and Things That Don't by David A. Adler, illustrated by Anna Raff, read to you by Jalen Gibbons. Our world is covered with rivers, lakes, seas, and oceans. More than 2/3 of the surface of the earth is covered with water. Before there were planes, people traveled across oceans from one continent to the next. They traveled and moved things over rivers and across lakes. Of course, before they could travel or move things by water, they had to know what things float and what things don't. A large boat that might weigh thousands of pounds will float. A whole crowd of people could be on that boat, and it would still float. But if one of those people dropped a small pebble into the water, that pebble would sink quickly. Pebbles don't float. You could have fun guessing which things float and which things don't. Fill your sink about halfway with water. Get a penny. A penny doesn't weigh much, but if you put it on the surface of the water, it falls right to the bottom. It doesn't float. Get an empty plastic soda bottle. Fill it about halfway with water. It's much heavier than a penny, but see what happens when you put it in the sink. It floats. Find things around your house, things that won't be damaged by water. Make a list of what you found. Next to each item on the list, write whether you think it will float. One by one, put each item in the sink. How often did you predict correctly which things float and which things don't? It's not just weight that determines whether something will float. It's also the object's size and shape. Get a piece of aluminum foil. Form it into a very loose ball. Place it on the surface of the water. It floats. Now crush the loose ball into a very tight ball. Place it on the surface of the water. It sinks. The aluminum foil weighs the same whether it's a loose or a tight ball, but the second ball takes up a lot less space. Its density, its weight relative to its size, is much greater than the first ball. The density of the second ball is greater than the density of water. That's why it sank. What's the density of water? Have you ever filled a bucket with water and tried to lift it? Water is heavy. A cubic foot of water, enough water to fill a box 1 foot high, 1 foot wide, and 1 foot deep, weighs a bit more than 62 pounds. That's a lot. Something has a lower density than water if it weighs less than 62 pounds per cubic foot. Something with a lower density than water will float. Do apples float? 1 cubic foot of apples weighs about 40 pounds. That's less than the density of water. Apples float. Does a bar of soap float? 1 cubic foot of soap weighs about 50 pounds. That's less than the density of water. Soap floats. Does clay float? 1 cubic foot of clay weighs about 100 pounds. The density of clay is much greater than the density of water. A lump of clay does not float, but clay can float. Get some modeling clay. Place a lump of clay on the surface of the water in your bath. It sinks. Now let's make it float. Shape the clay into a boat. Place the boat on the surface of the water. Does it sink or float? The lump of clay and the boat made from it weigh the same, but the boat takes up more space than the lump of clay because of its shape. The boat encloses air. The density of the boat and the air it encloses is less than the density of water. That's why it floats. Now with the clay boat in the water, take a look at the side of the boat. The boat is not really floating on the water, it's floating in the water, part of it beneath the surface. Put a few coins, marbles, or pebbles in the boat. As the boat and its contents get heavier, more of the boat goes beneath the surface. As the clay boat sinks lower, it pours water aside. It displaces water. The weight of the water the clay boat displaces equals the weight of the boat and its contents. Because of the shape of a boat, part of its contents is air. The boat will continue to float if the density of the boat and its contents is less than the density of the water. Steel is about 8 times as dense as water. A cube of solid steel would quickly sink, but the hulls of large boats are made of steel. Boats made of steel float because of their shape. Now get some ice cubes. Drop the ice cubes in the sink. They float. Why does ice float? Ice is water. Icebergs are huge, floating mountains of ice found in the colder parts of the world's oceans. Why do icebergs and ice float? You can find the answer in your freezer. Put some water in a paper cup. Make a mark on the side of the cup to show the level of water. Put the cup in the freezer and wait until the water has completely turned to ice. The level of ice is higher than the mark you made on the side of the cup. When water freezes, it expands. Ice weighs the same as water, but ice takes up more space. The density of ice is slightly less than the density of water. That's why it floats. Not all water is the same. Have you ever been to a beach? Was the beach at the edge of an ocean, or was it on a lake? Ocean water and lake water are different. Ocean water is salty. Lake water isn't. Ocean water is denser than lake water. Some things will float in an ocean but sink in a lake. You can prove that density of salt water is greater than the density of plain water. Get an empty plastic soda bottle with a cap. Fill the bottle about halfway with water. Mark the side of the bottle to show how much water is in the bottle. Now add about a teaspoon of table salt to the water. Put the cap on the bottle and shake. If you check the level of the water, you'll probably see that it does not change. What happened to the salt? It dissolved. What was once plain water is now salt water. It takes up the same space, but there's more to it. If you checked, you'd find that it weighs more. The density of salt water is greater than the density of plain water. Of course, the saltier the water, the greater its density. Different things have different densities. Even different kinds of water have different densities. That's why some things float and some things don't. The end.
Hi everyone, Mrs. Swearingen here with AVUSD Storytime Science. These are my assistants, Eli and Gavin. In the story, Things That Float and Things That Don't, you learned about density and flotation. The density of a substance is its mass per unit of volume.
I think I found the equation for it.
Yes, that's correct, Eli. Density equals mass divided by volume. In other words, it's the number of molecules in a given area. The more molecules you have in a given area, the more dense a substance is. So for example, we have some action figures here on a plate. This larger plate has a bigger area and there are 10 action figures on it. So the action figures are more spread out. This plate would be less dense than the smaller plate here with 10 action figures as well. If you notice, the action figures here are more crowded because they're in a smaller space. Therefore, they are more dense. In the story, there were a lot of examples of experiments with density and flotation that you could try at home. We're here to show you some more experiments that you could try at home, of course with your parents' permission. So this activity is called hot water and cold water density. The question you're trying to answer is what will happen when we mix the hot water and the cold water together. Ask yourself, what do you notice and what do you wonder? The materials you're going to need for this activity are some mason jars. You're at least going to need 2. You're going to need some mixing spoons. You'll need 2 different colors of food coloring. You'll need some cold water and some hot water. You're also going to want to make a laminated index card. So what you can do to make one at home is take an index card or a thick cardstock piece of paper. It needs to be large enough to cover the opening of the mason jar. You take some packaging tape, go ahead and coat both sides, front and back, and you will have yourself a laminated index card. Okay, for the procedure for this, we're going to start out with 2 mason jars. Eli, my assistant, is going to pour hot water into both of these mason jars. I'm going to do this demonstration twice, so I have 4 mason jars. Very good. Safety tip right here, don't make the water boiling, but do make it warmer than warm temperature. We're then going to fill the other 2 mason jars with cold water, and I made ice cold water and removed the ice before we began. Now I'm not filling all the mason jars all the way to the top yet because we're going to need to stir in the food coloring. I am going to go ahead and color the hot water red, red for hot. Eli, could you please mix those in? And I'm going to color the cold water blue. Let's make that a little bit darker. And I'm going to mix the cold water. Very good, Eli, thank you. Now I'm going to top these off where I'm filling them all the way to the top for the next step. So fill it as high as you can without spilling it. Now for this next step, I'm going to take it over to a sink because sometimes it doesn't work out well and goes everywhere. So watch as I demonstrate the procedure of what to do.
Wait a minute. Did you forget something?
Yes, and you might need a towel because you might fail the first time. Put the index card on the top of the mason jar and watch as I do the rest of the procedure.
Okay.
As you notice, the hot water and the cold water do not mix. The cold water is more dense than the hot water, so the cold water stays on the bottom and the hot water stays on top. Now try this by flipping it around.
Folks, now we're gonna try this again with the hot water on the bottom and the cold water on top.
As you can see, if you look in at the color, you can see the red water moving up and you can see the blue water mixing down to show that the hot water rises and the cold water sinks. Eli, can you help me explain the science behind this to our friends here at home?
An interesting fact is that the temperature can change density. Molecules in hot water move faster than molecules in cold water. Hot molecules, water molecules, bounce around faster.
They leave gap between the molecules when it moves around faster. And cold water molecules bounce around slower, leaving less gaps between them, making them more dense. As you can see, the cold water remains at the bottom because it's more dense, and the hot water remains at the top because it is less dense. When we reversed this and had the hot water on top, you instantly saw the mixing of the hot and the cold water. The hot water began to rise and the blue water began to sink, making purple water. We colored the water so you could see this visual happening. So this is the Klutz-proof density column. The question is,
why don't the layers mix?
so the materials that you are going to need, you're going to need a mason jar with a lid. If you don't have a mason jar at home, any clear container with a lid will work, like a water bottle. You're going to need a drop of food coloring. You're going to need water, vegetable oil, isopropyl alcohol, preferably 91%. If you don't have 91% and you only have 70%, we'll tell you what to do. And you're going to need non-iodized salt or kosher salt. You also might need a rag to clean up any messes. So the first thing you're going to do to create your Klutz-proof density column is that you are going to pour equal parts of the three liquids, water, oil, and alcohol, into the jar. So you're going to also need some sort of measuring cup or measuring spoon for this. Gavin, are you ready to help? I'm going to pour and you can go ahead and dump it in the jar. We're going to pour our water first. Next we'll pour in our vegetable oil. And then we will pour in our isopropyl alcohol. Go ahead and hold that for me, Gavin. As you might notice, the layers are already starting to make themselves out. We're going to go ahead and put in a drop of food coloring to help us to see the layers. And we're going to put our lid on. Gavin, go ahead and give it a little shake. Now, as it settles, it will begin settling into 2 different layers instead of 3. And in order to see the 3 layers, we need to add salt. You're going to add enough salt to where when you keep stirring that there's a little bit left at the bottom. Okay, Gavin, go ahead and stir that salt in for me. We're going to go ahead and add a little bit more. And then you go ahead and check the bottom and make sure that almost all of it's dissolved with a little bit left. If there's some left on the bottom, that's okay. And then what you're going to do is put the lid on it and be patient and let the layers begin separating out. When it's all done, you should have 3 layers that look like this. Now here's the science behind it.
It all comes down to density.
So after you wait about 10 minutes for your column to settle, you will notice that you have 3 distinct layers. And if you didn't get 3 distinct layers, it just means that you need to add more salt, stir it again, and go ahead and wait and watch what happens. So the bottom layer is our water layer, the middle layer is our oil layer, and the top layer is our alcohol layer. And like Gavin just told us, it all comes down to density. The water with the salt dissolved in it becomes our heaviest, most dense layer. The oil's the next dense, and the least dense layer is the isopropyl alcohol. So why add the salt? The reason we needed to add the salt is without that, you only got 2 distinct layers. We had to do a procedure called salting out. Isopropyl alcohol and water are both hydrophilic or polar molecules. Oil is a hydrophobic molecule. Without adding salt to it, the alcohol and the water combined. But once you add salt, the salt ions bind to the water molecules and you're able to see 3 distinct layers. So no matter how many times you shake this column up, it will always settle back out into its 3 columns.
We hope you had a lot of fun with these experiments of density, and make sure to try the challenge. Don't forget to like and subscribe to this channel and hit the bell and the notification box.
So make sure you take pictures of the activities you created and the challenge that you did and post them on social media with the hashtag AVUSD Storytime Science. Thanks for joining us.